The source of energy that stores energy as chemical energy, and then we get out electrical energy from the battery. Oops. I don't know where my cursor is. There we go. Okay, we're going to watch this video. If it'll open. This is just a short YouTube video on how a battery works. Needs to affect chemicals on possible. Let me just scoot up. Here we go.
You probably know the feeling. Your phone utters its final plaintive bleep and cuts out in the middle of your call. In that moment, you may feel more like throwing your battery across the room than singing its praises. But batteries are a triumph of science. They allow smartphones and other technologies to exist without anchoring us to an infernal tangle of power cables. Yet even the best batteries will diminish daily, slowly losing capacity until they finally die. So why does this happen? And how do our batteries even store so much charge in the first place? It all started in the 1780s with two Italian scientists, Luigi Galvani and Alessandro Volta, and a frog. Legend has it that as Galvani was studying a frog's leg, he brushed a metal instrument up against one of its nerves, making the leg muscles jerk. Galvani called this animal electricity, believing that a type of electricity was stored in the very stuff of life. But Volta disagreed, arguing that it was the metal itself that made the leg twitch. The debate was eventually settled with Volta's groundbreaking experiment. He tested his idea with a stack of alternating layers of zinc and copper, separated by paper or cloth soaked in a saltwater solution. What happened in Volta's cell is something chemists now call oxidation and reduction. The zinc oxidizes, which means it loses electrons, which are in turn gained by the ions in the water in a process called reduction, producing hydrogen gas. Volta would have been shocked to learn that last bit. He thought the reaction was happening in the copper rather than the solution. Nonetheless, we honor Volta's discovery today by naming our standard unit of electric potential the volt. This oxidation-reduction cycle creates a flow of electrons between two substances, and if you hook a light bulb or vacuum cleaner up between the two, you'll give it power. Since the 1700s, scientists have improved on Volta's design. They've replaced the chemical solution with dry cells filled with chemical paste, but the principle is the same. A metal oxidizes, sending electrons to do some work before they are regained by a substance being reduced. But any battery has a finite supply of metal, and once most of it has oxidized, the battery dies. So rechargeable batteries give us a temporary solution to this problem by making the oxidation reduction process reversible. Electrons can flow back in the opposite direction with the application of electricity. Plugging in the charger draws the electricity from a wall outlet that drives the reaction to regenerate the metal, making more electrons available for oxidation the next time you need them. But even rechargeable batteries don't last forever. Over time, the repetition of this process causes imperfections and irregularities in the metal's surface that prevent it from oxidizing properly. The electrons are no longer available to flow through a circuit, and the battery dies. Some everyday rechargeable batteries will die after only hundreds of discharge-recharge cycles, while newer advanced batteries can survive and function for thousands. Batteries of the future may be light, thin sheets that operate on the principles of quantum physics and last for hundreds of thousands of charge cycles. But until scientists find a way to take advantage of motion to recharge your cell battery, like cars do, or fit solar panels somewhere on your device, plugging your charger into the wall rather than expending one battery to charge another is your best bet to forestall that fatal bleep.
Okay, I think that's interesting. How many of you have a battery with you right now? Okay, all of us should. If you have a phone, you have a battery. If you have a Chromebook, you have a battery. Okay, so batteries are a big deal. And that's an area of research. So if you go to work at a company and they're looking at batteries, that's a big deal. We're trying to find batteries that last longer, batteries that don't get so many defects when you charge and recharge them. So if that's interesting to you, you could major in something like material science, and that would be a field where you would learn about battery materials. Okay. So they talked about two different types of reactions. We have oxidation and reduction. So these oxidation reduction reactions move electrons. Okay, that's what they're doing. And so that's how we get from chemical energy into electricity. Anytime you move electrons, you're getting a current. How many of you guys took physics? Does that sound familiar? If you have an electron that's moving, you have current. Okay, and that's electrical energy. The chemical reactions in a battery are called oxidation reduction reactions, and we also call them redox reactions. So a shorter way to say oxidation reduction is just redox. Okay. So if you ever hear somebody talking about a redox reaction, they're just talking about a reaction that moves electrons. Okay. All right. So we have two reactions up here. You won't have to look at this. You won't have to worry about this too much. If you take Chem 1110, this is something we talk a little bit more about. But for us, what we care about is when we lose electrons, this is oxidation. So, oops, I want my writing tool back. Yes, and I want to go back a slide. Okay, so this one is oxidation. This one is reduction. So you need to remember this part. You need to remember oxidation is losing electrons. Okay, and reduction is gaining electrons. Okay, so I remember this using this acronym. Oxidation is loss, reduction is gain. So oil rig helps me remember oxidation is losing electrons, reduction is gaining electrons. That's how I remember that. Okay. All right, questions? We're good so far? So these are two types of reactions. So here we have a metal, and the metal is losing electrons, so the metal is being oxidized, and this is what they're talking about in their battery in the video. So copper is being oxidized, and then I think they were doing zinc actually. Silver, this is silver. If it gains electrons, that's being reduced, then it turns into a metal. Okay, we talked about that. All right, so we're going to build a battery up here. I think I forgot something. We'll start this. So I have this clock up here. And I have taken out the battery. So I don't know if you can see that very well, but I've taken the battery out. And I put these wires here. And we're going to build a battery out in the front. Okay? That's why I'm spinning this time. Okay, can you guys see our clock? All right. So we're going to build something like this. Ours isn't going to be as technologically advanced, but we're going to make something that works. So I have my chemicals up here. I'm going to put them on a tray in case I spill. And I have some copper. So I'm going to pass a piece of copper around. This is kind of interesting. Try not to break it, but you can kind of feel how it's pretty soft. And then we're also going to use magnesium. So this is a piece of magnesium. Let's have a little bit of this. There we go. So you can fill this magnesium. That's magnesium metal. It has a little bit of oxidation or kind of like rust on the outside. And what we're going to do is we're going to take some, so I'm going to take my copper, I'm going to put it in this one over here. So this would be, this is one of my cells. Okay, I'm going to put some copper sulfate with the copper. Fill that up. Okay. And I'm going to hook it to this side of the clock. I think this is, oh no, I need to hook it to this side. Okay. And that way. So I'm just going to hook this alligator clip to my copper. And then I have some magnesium ribbon. That's what they call this when you buy it. It's kind of ribbon-like, I guess. And I'm going to put this magnesium into my beaker. And I want that in there, pretty good. Okay. And I'm going to also hook this one up to my alligator clip. Wait, first I'm going to, oh, I guess I'm going to put my magnesium sulfate in there first. Okay, fill it up pretty good. Okay, now I'm going to clip it up. Let's see what, hold it up there. Okay, is anything happening with the clock? Okay, so what should happen is our electron should move from magnesium through to the clock, to the negative side of the clock, through the clock, make the clock work, and go back out to our copper. So we are missing something here. You guys think of what we would be missing? What's wrong with our circuit?
It's still open.
It's still open. Perfect. So this is the part I forgot. So I'm gonna go grab the part that closes our circuit. All right, so I have this. This is going to be our salt bridge. This hot dog is going to connect our circuit. So I'm going to take that, I'm going to stick it in our solutions. We should see our clock work. Okay, so now our electrons can go from our magnesium through the wire, make the clock go. Now that we have a closed circuit, our electrons can move all the way to the copper. And then through this salt bridge, we have ions that are going to balance the charge of the electrons. Okay, so electrons are negatively charged. Things don't like to move if they have to have a negative or a positive charge. So we have to balance the charges as they move back and forth. Okay, so we are going to draw, this is working much better than yesterday. Yesterday it just got stuck. So this is much better. Okay, so we are going to label the parts of a battery. Okay, so we're going to label it like, ours will be a little bit backwards. So over here, we have our anode. So at the anode, the reaction that's happening at the anode is oxidation. So I remember this because anode and oxidation, they both start with a vowel. So that's how I remembered that. Oxidation happens at the anode. So our anode is on the wrong side. But our anode is this magnesium strip. The electrons get stripped off of the magnesium and they go through the clock and they end up at the copper. Okay. So today our anode, we could write that. Our anode today is magnesium metal. If you want to remember that. Okay, so then at this anode, oxidation happens at the anode. And I'm going to remember oxidation is loss of electrons. So electrons are going to be leaving. And I noticed up here we have our arrows. So electrons are leaving the anode. Okay, our electrons leave the anode. And then this is just a symbol for a device. So we've put a clock in here as our device. But you could also put like a blender or your computer. So, woo! I guess blenders don't usually run on batteries. But this is just your device. And we're using that current to get some work out from our electricity. So our electrons travel around the circuit, and we get over here to our cathode. This is called the cathode. And I remember that reduction happens at the cathode because they both start with consonants. Okay, so we got vowels over there, consonants over here. And I also remember that the cathode must be this one because reduction is gain. Electrons are coming over here. The cathode is gaining electrons. Okay, and then like we talked about, the electrons wouldn't move unless we can balance those charges. So we have a whole bunch of negative charge that must be balanced. So the positive charges are going to flow towards this negative charge, and negative ions are going to flow over here to balance the charge over there. Okay. And this device, what we use as our hot dog, is called the salt bridge. So this is just a fancy way to balance our electrons. Okay. So electrons are not going to be flowing through here, just the ions. Okay. Another thing that we need to remember is electrons are traveling here. What else is going to happen at the cathode is if we left this piece of metal in for a long time, we would start getting a thicker piece of metal. So we are going to get deposition. We're going to get metal deposited. I'm not sure how to say that. We'll put deposit metal. We are going to eventually, our cathode will grow thicker and thicker. It's going to take a while because we just have little atoms that are floating around. But eventually our cathode is going to get thicker, and we could also write it's going to get heavier. Okay. And the opposite thing happens at the anode. So both electrons are leaving the anode, and we are going to have ions are leaving. Ions leave the anode, and eventually our anode, if we left this in for a long time, our anode would completely dissolve. This is going pretty good. It's getting a little bit stuck. Okay, questions. So this would be something like on the test, you could see the flow of electrons and you'd have to decide which one's the anode and which one's the cathode. So electrons flow towards the cathode, away from the anode. And this is really helpful. Oxidation is lost. Electrons leave the anode. Electrons go towards the cathode. Okay, questions on our diagram? Okay. All right, I also have this in there if you need to go back and look. It is on the slides. All right, so we can look and decide which metals will give a better anode and which ones will give a better cathode. So we could look at something like this. If the metal is at the top, this is called our activity series. These metals are more active. They want to give away their electrons. If they're at the bottom, they're not very active. They want to keep their electrons. Okay? So a question might be like, oh, potassium really wants to give its electrons away. What kind of, would it be a better anode or cathode? So if you're giving your electrons away, oxidation happens at the anode. Oxidation is lost. Something up here would be a better anode. And if it wants to keep its electrons, that's going to be a better cathode, like the copper up here. Copper wants to keep its electrons. Copper is here. Copper is going to be a better cathode because it wants to keep its electrons. It wants to be reduced. Okay, so it's going to be a better cathode. Okay. All right, so we are going to go into the lab and we are going to make a penny battery. So we're going to use pennies as our cathode. So copper is going to be our cathode, just like up here, cathode. We're going to use aluminum foil instead of magnesium as our anode. And then our salt bridge, we're not going to use hot dogs. I guess we could use hot dogs. But we are going to use paper towel. I cut up some paper towel holders, the rolls, the cardboard stuff. And we're going to soak that in salt water, and that's going to be our salt bridge. Okay? So one group got this to work yesterday. They were using old cardboard, so I would cut new cardboard. They were also not very careful. So this is a lab where you need a little bit of finesse. So you need to be really careful, and it matters if it's messy. If it's really messy, then the electrons are not going to like your circuit. So try to be as careful as you can. What we're going to do is we're going to try to light up an LED, and we're going to take a penny and then a cardboard piece soaked in salt water, and then foil. And that's going to be one cell, and then you're going to stack another cell on top of that. So then penny, cardboard, foil. And you can make a little tower. So last year it took people about 8 to like 12 pennies. So in their stack, so penny, cardboard, foil, they needed about 9 to 12 pennies to get their LED to light up. So see if you can beat last year. See how many pennies you need to get your LED to light up. The other thing is an LED is directional. Let me grab one and show you. So this is an LED. I'll walk around and show you. One of the legs on the LED is longer than the other one. So LEDs, it matters which direction you put it in the circuit. So if you try for a while and it's not working, try to switch the direction. From what I understand, I think the long side should go on the foil. The long side should be with the anode, and the short side should be with the cathode, the copper. But if that's not working, or if you're confused about the long side, you can always switch the direction of the legs. Okay, so there's our LED with the legs. So LEDs are also directional. If you put an LED on a voltage and you have it backwards, that can burn out the LED, which is fine. We have lots of LEDs. So if you think your LED is not working, we can switch out your LED. Okay. All right. I also remembered just now we have multimeters, so you can check and see how much voltage your penny stack is giving. All right, so our goal today is we are going to try to draw a schematic. So as a scientist, you are responsible for explaining your work and explaining what you did in the lab. So I want you to draw a schematic of your stack, okay, of your stack, and then make sure you label at least one of the cathodes, an anode, and a salt bridge, and then show the electron flow. You should be able to figure out the electrons should be moving in a direction around your circuit, so make sure you show that. And then report how many pennies it took, and then also report what you think could be improved. on your battery. Okay, so we're going to get into groups, so make sure you find a group. And I've made new foil circles and I made new cardboard circles. So use the new stuff, I think that'll be better. Also try to be careful and we'll see how it goes today. So I would probably bring my notebook in so that you can draw your schematic and then we'll have the rest of the time to do that. All right, perfect.